We know that meteorological events and unusual weather affects energy production. But it's not just extreme incidents like heat waves and storms. Anything that's considered unusual for the specific climate can influence the industry. Take the mild and dry winter that northern Italy experienced in 2015-16 as an example. Warmer than expected temperatures during the winter season resulted in lower levels of snowfall than the industry had originally planned for. This reduced their hydropower production to almost half of what they expected in the spring and summer months. The SECLI firm project can help address the risk of impactful droughts like these by analyzing data to predict how much snowmelt is available for summer hydropower production. This, together with seasonal forecasting methods, can help operators make more informed decisions and improve their strategic planning. Visit the website and read the case studies to discover the different ways that the SECLI firm project could help your business mitigate unusual meteorological activity.
So we see just an agenda. So basically we are dissecting scenario part 1, so from the point of view of Enel. And then we are going to tell what happened, what's the context in terms of market and climatology. Then we go to a second session of results. So in results, the point of view of meteorology and also point of view of market. So the results of portfolio management. Then Alperia will join us in the presentation, and they are going to explain the setting scenario from the point of view of Alperia. This section 3, I would say. Then Jurak is going to talk about the downscaling runoff seasonal forecast methods applied for Alperia, and finally the results in terms of value from Alperia, and finally a last section about the trial climate service that we implemented in the project. So we can proceed. Thanks. So case study 2. This is just an overview. So the target period was the Q4 2015, so October, November, December 2015, and Q1 2016, so the winter basically. The main variable was the total precipitation, so we mean liquid and snow precipitation. And as we already know, we have involved the two industrial partners, so us, Enel, and Alperia. And we see this chart of the whole case studies of the SECLI film project. This case study so basically is located in northern Italy, as well as for Enel as for Alperia. So we can proceed. Next slide, please. Thanks. So just to recall, so case study 2 is a very complex case study, and to understand the whole context, we have to start 6 months earlier. I would say in July 2015. So when we had a very hot summer, case study 1. Why I say this? Because when we had a very huge peak power consumption that you see this green square on the top center plot, basically all the power utilities has been forced to run at the maximum their generation. So I mean that hydroelectric utilities has run at a very high level their turbines, so they consumed water reservoir. So we have a premises to do. So this sum is a part of the story. So basically, and also they forced by the TSO because of the problems of the stability of the national grid. So we have been very close to the maximum capacity production in Italy. So, and also very high prices, so it was a good opportunity to make money. So that's we have at least 2 good reasons to run our water turbines and to empty the reservoir. We can go, so next slide, please. So now we go directly to case study 2. So just a few words about synoptics. So basically, we have a very long-lasting positive anomaly of geopotential over Europe. You see on the left images taken by NOAA, and we see here the anomalies of 500 hectopascal from July 2015 to December 2015, and we see with very strong positive anomalies. And the consequence was a very long-lasting draft. You see on the center images, that's an anomaly of precipitation taken by the GPC GPC measurements by NOAA. And you see these strong negative anomalies over the Alps, a part of the central Italy. And so it's quite clear that we had a quite important lack of natural resource. So basically, as you can see on the left side of the right picture, so the red circles, you see the red curve was the actual production, and the gray shading was the, let's say, a normal production. So we have been very below the normal production because just we went out with the water, so we had no water. So that's the context. 2015 has been an exceptional year for Italy, I would say also for Europe. So we had again in summer extreme temperatures and then this very prolonged scarcity of precipitation. So a combination of problems, I would say. Next slide, please. Okay, so we see again the lack of hydroelectric production, but we have also to say something. So if you look, take a look on just the market, on market behaviors, so we don't see anything pathological like for case study 1. So you see the case study 1 was a quite obvious event. So we have a very peak. We lost the axis. I don't know why. Anyway, basically we have the plot on the right shows the prices per euro per megawatt per hour for gas in blue and power in yellow. So there are the prices in euro per megawatt per hour. You see the peak for case study 1 that went up to 100 euro per megawatt per hour, in July 2015. That's quite obvious. So we have a strong power demand. The demand exceeded the supply, so the prices spiked. During the winter, that is the blue box, you don't see any spike or pathological events. So it's quite strange. So looking to these plots, it seems that nothing happened especially. That's not true because Enel is a large company with a mixed portfolio of production. So we have hydroelectric production, renewable like wind, photovoltaic, but we still have an important portion of fossil production, coal and gas. So if you have no water, you have to run your traditional fossil plants. And so you have to make a plan of eventually to buy or not the fuel. And that complicates a lot of the problem. So we have not only a problem of lack of natural resource, but we have a problem that we have to connect the meteorological event with the market situation. So you see, for example, that for November, basically on the center of the blue square, we see that the prices of power, so the yellow curve, went up a bit. And so we see a small effect of this lack of supply because of lack of hydroelectric power. So we have a small increase of the prices. So it's nothing that can be related with a huge spike of July. Anyway, some effect we have seen some effect. So the problem is to make a plan. So to have a correct forecast in order to plan the action to be taken on the market. So most of the production is on the Alps. Hydroelectric power production in Italy is about 40% of the total renewable production, and about 25% of the total production, so with also the traditional fossil. So when we have multi-utilities like us, we have a problem, for example, that we sign contract to give energy to a customer. So we promised that energy to someone to deliver at some date, let's say next 3 months. Now I have to look for the energy, and I have basically 3 choices. Or I have the energy, so I'm sure that I'm going to produce the energy, so that's fine, easy case. Or I have to buy the fuel to produce the energy. Or I can go to the market and buy the energy from a counterpart. Anyway, I have to take a decision, so I have to do something. So to cover my contract, we say as a jargon term, to cover my selling contract, or I can have the opposite. So if I forecast more energy that I was forecasted previously, I have some energy that I didn't sell yet, and so I have a risk of the price, and so I have to take some action also in this case. Next slide, please. This is just a technical technicality. So basically, as many of you know, the seasonal forecast as well as more the analysis are gridded data. So we have data over our geographical grid, mosaic, but our econometric industrial models works by mean time series. So we have to transform geographical geolocated data to a time series. So they want the forecast for the whole Italy, for example, for temperature and power demand, the center box. So just one index. Or for example, for Alps and Apennines, we look for 2 time series. So we had to define our geographical domains to make the aggregation, and also to use the multimodel. So to have a, let's say, semi-probabilistic or weighted average of the from the members of the model, especially for the case of multimodel. So SECLI basically is as a mainstream of a single model test, the System 5, or multi-model test using also the if I remember, some other models. But you have to aggregate specially and then to construct your ensemble. And then you have to pass the information to your econometric model. About this, you have to spend other few words. So we know that the best use of a seasonal forecast model is a probabilistic approach. And it was a very interesting discussion, intense, I would say, exchange between industrial partners and scientific partners, because the proper way to use it is probabilistic. But in a corporation, it's not that easy to use a probabilistic approach, because at the very end, you need to take a decision, a binary decision on the market. You have to buy, to sell, or to do nothing. And at the very end, you need to construct a deterministic scenario that you know that maybe is wrong, it's not the best way, but at some point you have to go to the top management and to provide them a scenario, at the base scenario, a probability maybe, but you need to, so we had to take a compromise, maybe not very scientific, but we must to take a compromise between a pure probabilistic approach and to provide us, let's say, a deterministic, that is not the best way, I know, scenario from seasonal forecast for the random models. That's the main setting scenario. So we see the methodological scenario, just a overview the market scenario. Now we are going to make a deep dive in the results and some other more deep dive on how it works power utility. This slide tries to explain again what I told before. So what is the risk management problem? So one word, it's quite obvious to say that the first goal of a corporation is to make money, to make profit. Yes, but to make profit, the really first urgent action is to reduce the risk. So we have 2 parallel jobs. So to try to buy cheap and sell high, basically a product, that's quite straightforward. But when you buy into you sell, so when you take action in the market, you take a risk. So without risk, there is no business, but you have to reduce it. So maybe the most important, I would say, the effort on my team and the people that work with me is to reduce the risk. When you make a good job for risk management, I would say that you automatically make money or something like this. So at least you don't lose the money. That's, I would say, the most urgent goal. So the weather acts to the power utility in 2 ways. A direct way by power demand again. So the temperature acts directly on power demand, and I would say also the gas demand in the winter for heating. And you have also an indirect impact to the action to the thermal system. So if I have a strong production by wind or by rainfall, so hydroelectric, maybe my thermal plants are kicked out from the market because they are costly. I have to take into account this, even to make a plan. So we have basically a price risk, so the price just of the power, what we sell, and a volumetric risk. So if I have a few rainfall, I can produce a few power. So I have a lack of volume. Maybe I have a high prices, because also the market is, I would say, tight. So the market is nervous and the prices are high. But by the way, it's not easy. So basically, we have two variables that are not really independent. So that's a good question. And we have to manage both of them. And we have the complication that also that we have to take in account of the commodity market. So you have to make a relationship with the weather and commodity, because at some time you need to buy gas or coal or other commodities. So I just trying to make you a picture of the complexity of the problem. That is basically a multivariable problem, almost independent. This is rather complex, but it's the same story. So basically, you have the full basically workflow. So at the left, in the left, you see the variables. So the power demand, renewable. So basically climate-driven variables. But then you have the problem of the bottlenecks by the net grid, competitors building strategies, so how the competitors work. Commodity prices, regulatory, but the framework maybe is less. Then you have to add models. So at some time you have to simulate this complex world, and to simulate also your availability. And then you have to estimate your risk factor, and finally to take decision. That's the hedging strategy. And they take decision to the market based on the scenario, simulated scenario, that is a future scenario. So again, at some time you need to propose a scenario that you believe, maybe not too much, but some kind of scenario. For example, now we are asking together if the next winter is going to be cold or not. And at some time you must to say something. So maybe yes, with a probability, but you have to produce a scenario, a given scenario that will produce a given scenario of prices, and finally you will take the decision. So that's maybe the process. This is the slide for the first most obvious point where the weather variables enter. So just at the beginning of our flux, so just to supply the first variable to supply our industrial and econometric model. So we have weather variables. We simulate the renewable production and the power demand. Then we put the simulated power demand and power production to the optimizer, so a model that get the minimum cost result. And finally, we get the implemented scenario. So you have a forecasted scenario of the market. Then at this point, you have to take your decision. So you have the future price of the power, future prices of the commodities, forecasted commodities, also the, I would say, covariance problem. So any action that you do in the market affects the market. So the model needs to have a feedback. So if we put a lot of energy on the market, and we are a big player, we change the price because you change the system. And so the model needs to try at least to simulate also your own effect on the market. That is not easy, actually. But this is the first point. Second point is an action that can be done at the very end. So one way to mitigate your risk is to use the weather derivatives that now are quite common used. So as a direct contract, I would say, direct contract between two counterparties that decide to sell, for example, energy decided over a temperature over a same place, for example, temperature over Milan, with a scale that is decided by the two counterparties, a contract. In this case, you can cover your price problem. So if you, I don't know, if you forecast an increase of a price, you already maybe sold your power, so you basically cannot take more money. You make maybe you can try to sign a weather derivative. In this case, we have I would say a direct action of the seasonal forecast. So the people want to say to understand what could be the future. So this is a direct action to the portfolio management at the very end of the process. So you see, the slide before was at the beginning of the process, so at the simulation level. Now we are on the desk, trading desk of the process, so at the very end. This formula is what we defined the performance indicator. So a metric that we try to set to to test in a numerical way, objective way, the efficacy of our experiment. So SECLI film used basically as a two-way approach. So the basic scenario, that is how we already do the things by mean normal values. So you use as a forecast for the next months the normal values, yes, the climatology. And the test is the seasonal forecast. So we have the difference between the margin and the profit at risk. That's the portion of the profit that is still exposed to the risk of the market. I mean, basically, I'm simplifying, but just to try to be clear, if I forecast 1 kilowatt per hour of production, and let's say that I'm sure that I'm going to produce 1 kilowatt per hour for the next months, maybe I can sell half of this 1 kilowatt, so 500 watt per hour to someone. So I sign a contract at some price. So half of my energy now is secured. The price is fixed. I have no risk. I sold it. A client bought this. Maybe already paid forward. That's called forward contracts. I'm fine. I'm fine because I have no risk. But the remaining 500 watt per hour are still at the risk of the market, because I have the energy that I didn't sell yet. I can sell tomorrow, a week later, 1 month, I don't know, it depends. But it depends by the trend of the price in the market, because if the price of the market are going down, I have a problem. I have a big problem. So this half energy that I still have to sell is at risk of the market. And basically, I use the PAR, as index. What is the amount of my portfolio that is still at open risk? Of course, I can cover 100% of my portfolio. I can do this. But in this case, I'm going to renounce the possibility to make more money. And maybe that's a problem. So it depends. So the answer is not easy, because I'm sure I sold my energy. I'm fine. But maybe my competitor is more behave, say, and make more money, take some risk. So what is the right portion of the portfolio that I have to keep open in order to take opportunities? Nobody knows, of course. That's the main questions, and that's the work. That's difficult questions. So, of course, it depends on the market. For example, now that the market get mad, as you know, maybe it's not very, I would say, a good idea to leave open a big chunk of portfolio open. Maybe, I don't know. And anyway, this difference is the measurements of the performance. So how my forecast performed with respect the base case. So using climatology as forecasting system, or using seasonal forecast as a forecasting system. That's the test. Of course, now we will check this with respect to the actual data that we had a posteriori. So those are past case studies, so we can know how the history went, and to check to do a validation. Here, this is decision tree. That's a very, very important point and difficult point. So in a corporation, the decisions are taken by human being. So it's not, they are not taken by computer. It's not a program. So we will need a time machine to go back to July 2015, or I don't know, Q4 2015 with our management again. That's possible, obviously. So we needed to produce a Boolean version of this holistic process, a human process, in order to make it reproducible and objective. And that was the effort. So to try to make a reproducible experiment. So here we see the workflow that's very similar. So we have the ACWMF, so the system 5, and the -3, -1 example that basically are the 1 month before or 3 months before the event forecast release. Then the climatology, that was the basic test, and actual data. And after the decision-making process that we discussed by the workflow. So here we see some weather results. I'm going very quick here because they're already shown and some deliverable. But basically, we see temperature at the top for the Q4 2015, where basically the temperature has been forecasted quite well properly. The red bar is the actual data, and the blue and bars are made by System 5, and cyan bar is made by multi-model. And we see that for temperature, we have very good forecast. For precipitation, that is the middle, we had some problems. So the models had some difficulties to forecast the drought because the red bar is very low because we haven't got any rain. And basically also for the wind, the models had some problems so to forecasting. So we have a very high pressure system with a very low wind. That's typical for Mediterranean Sea. So here we can see the result for Q4 2015, as well as for the Q1 2016, we had a good forecast for temperature, where the models done very better than climatology. That's a good news. So they forecasted quite well temperature. They have done better than climatology even for precipitation because they forecasted more precipitation than climatology. But actually on Q1 2016, we had a lot of water, the red bar. So we have very important precipitation flux. And the same for wind. So we had a lot of wind and also here the models done better than climatology. So this is quite complex. So you see in this slide, again, this indicator, where I apologize, there is a refuse here, but basically the S is for seasonal forecast. The C, so the index IPC is for actual data. So we make a difference between the seasonal forecast with respect to the truth. So actual data, so actual scenario, and seasonal forecast, the climatology, that's E, expected, against, again, the actual data. And then we see that the M-1 was the best case. You see on the left the indicator and the difference of this margin versus PIR, and as well as for the plot below. So here we see a complex situation where basically we had the Q4 2015, where the main problem was the open position. So open position, we mean the forecasted energy that we have to sell. So for case of ACWMF that forecasted better a low level of hydro power, we had minus value of open position, this minus 7.3%. So we had less energy that we have to sell on the market. For the multi-model, unfortunately, the forecast was worse, and so we have more problems. In this case, you are going to over-hedge your portfolio, that's the risk, and that's something that you have to avoid. And we didn't catch the magnitude of the event. Okay, so basically, in the Q4 2015, the best estimation is represented by the valuation of 1 month, the target. So the 1 month before was better. And what do you expect? So usually the model perform better when you are close to the event. In case Q1 2016, we didn't have the time, sorry. But basically the -3 forecast was better because it didn't take an account of the actual drought of the last months of Q4 2015. And so was for a very, only a luck moment close to the actual data, where the actual data were for very wet winter. So in this case, just a causality. So it was a random effect. Okay, thank you very much. Now we have the URAC. Yeah.
Okay. Alberia is a small utility, small with respect to Enel, that is located in the northeast of Italy and in the province of Bolzano, in Italian. And we are a region where the high mountain is present, and so we considered that can be interesting to to take into account for applying this case study, a valley that is located in the southeast of our region and that is interesting by the presence of high mountains, because in the next figure you can see the zoom of the valley that we considered, and you can see how the high mountains are here present. And high mountains, it means that we have the largest part of the production that is concentrated in the summer period, in the spring or summer period, when we have the snow melt from the mountain. So in this valley has an interesting system of hydropower plants. Here we have 6 hydropower plants. In the next scheme, you can see a schematization of the system that here we have. There are 6 hydropower plants in series, where 6 turbine stations and 1 pump station. And for the SECLI film project, we focalized especially in the central basin that you can see in the image, that is the largest one, and that is called the Lago di Zoccolo Lake, and where its water is turbined by San Pancrazio hydropower plant. But then we extended our analysis on all the valley. So in the next slide, I put only schematic, some data about the system. So the total volume of basin here is 50,000 million cubic meters. The maximum total power is 250 megawatt, and the maximum energy per year is 319 gigawatt per hour. Alperia manages 38 hydropower plants in total, but this system is really important for our utility. So in the next slide, I represented a conventional hydropower dams. Here in this valley, in this system that I presented to you, we have only conventional hydropower plants. It means that we have the dams and we have artificial basin, more or less large, and it means that with this kind of hydropower plants, we can manage the production, and we can in such a way decide which is the volume that we want to have in the future. I mean, if we suppose that in the future we need a larger amount of production, we need to have a larger amount of volume of water in the basin. So it's interesting. This is a typical case where the management and the future prediction of inflows is really important, because to have a good forecast of the precipitations means to know the volume of water available for production. So my last slide. At the moment, Alperia uses a model for the management of the hydropower plants in all the region. This model is called HydroTool Misurio, and here you can see an example of the schematization of the Ulten Valley in this model. So, but the inputs that we need for running the model, for deciding the management of the plants in the future, we need the natural runoff in the basin, the initial reservoir level, the predicted energy price, and the obligations in plant management. So in this case, for the SECLI film project, the two more important data that we put as input in the model are the natural runoff in the basin and initial reservoir level, because this can give some better outputs. The outputs of the model are the reservoir water volume, which optimizes the energy production during the forecast period, and the energy production forecast.
Where the output of the state-of-the-art seasonal forecast system, such as ECMWF, for instance, that was used in this work, is of the order of 100 kilometer, and so in general 2 cores to reliably represent the small-scale features of local applications, and this could result in relevant biases of the forecast when applied for small scale purposes. And in the next slide, please, we started to assess, for instance, the overall bias of ECMWS System 5 seasonal forecast of mean temperature and total precipitation at seasonal aggregations with respect to ERA 5 over Europe. And here we consider just the reforecast over the 1993-2016 period. And here we see that in general for mean temperature, the seasonal forecast has a negative bias, especially in spring and winter, especially over mountain European areas. And as regards similarly for the seasonal precipitation totals, the amounts are largely underestimated by the forecast, especially in summer, and particularly over the mountain areas where the bias could be below minus 500 millimeter. So in this context, we set up a calibration, a downscaling framework, which could reduce such discrepancies, improve the skills of the forecast, and provide improved input information for the runoff modeling for the case study catchment. We wanted to build a scheme that could be easily applicable, replicable in other case study areas, but at the same time that could be able to provide accurate results. We focused on precipitation and temperature only as key variables, and we set this the scheme in order to deal with monthly aggregation, monthly quantities. So we considered for the implementation and validation the ECMWF System 5 forecasts of mean temperature and total precipitation over the incast period. These forecasts are available at 1 degree resolution. We cut them over European domain, and as reference we use the ERA 5 reanalysis over the same domain, same period, which is available at 0.25 degree resolution and spatial resolution. We decide to use the reanalysis instead of observations in order to assure as much as possible the replicability, let's say, or transferability of the method on other areas. So first of all, the forecasts were spatially disaggregated to the same grid of ERA 5, and then the bias correction was applied, and this provides the bias adjusted seasonal forecast and downscaled at the target resolution of monthly quantities. And more specifically, this spatial disaggregation was applied by implementing a simple bilinear interpolation for all ensemble members, all month and lead times, and then the correction was applied through empirical quantile mapping that was implemented for each grid point and applied for each month and each lead time separately. The calibrated fields were then, or maybe the accuracy of the calibrated fields was evaluated by the cross validation, by the comparison with ERA 5, and by using several verification metrics. For instance, here we computed the mean ensemble bias for each month and each lead time, and here we show the results just for the Alpine region where the case study catchment is located, and we clearly see that the original biased forecast is effectively removed after the downscaling, and the results here for both variables, and the results here are referring to January and July and to the lead time one only, but the same conclusions can be extracted can be valid also for the other lead times and months. In order to, so besides the Alpine region, we also applied, maybe evaluated the forecast, the calibrated forecast over the larger European domain in order to generalize a little bit the conclusions. And here, for example, we are showing the mean absolute error of the calibrated forecast with respect to ERA 5. With respect to the original forecast, the errors was largely reduced. And for temperature, the residual, let's say, mean absolute error is below 1.5 degree in all seasons, while for winter we have a bit larger values, especially in the eastern part of the domain. But for precipitation, the errors could be locally still quite large, especially in autumn and winter, especially over mountain areas and along the Atlantic coast, where mean absolute error could be still of several hundreds of millimeters. The general difficulty in improving the precipitation forecast was also confirmed by other verification metrics that we used. So here, for example, the continuous rank probability skill score, that is a kind of measure of the difference between the cumulative cumulative distribution function between observation and forecast, and value above 0 are reporting increasing of the skills, and negative values are reporting degradation. And here we see that for temperature in general we have some increase of the skill of the calibrated forecasts, especially in spring and summer, and in some cases with also statistical significance. But for precipitation, the increase of skill is quite limited and mainly occurring in spring. And finally, we also compared the calibrated forecast with the output of another downscaling method, Adamant, that is a downscaling scheme developed by Meteo France that deals with daily quantities and apply a quantile mapping conditioned by weather regimes by using ERA 5 as reference as well. And the comparison aimed to assess the limitations and benefits of the proposed method in improving the forecast with respect to more sophisticated or complex schemes. So here the two outputs were compared on seasonal scale for temperature and precipitation over a European subdomain by considering the same period, of course. And here we can observe that in all cases, so all seasons, all lead times, and for all verification metrics, the performances were quite similar between the two. So we can summarize that, first of all, the downscaling and bias adjustment are essential procedures in order to reduce the general discrepancy or the potential bias that could affect the original forecast before their application to, let's say, to specific purposes. The applied or developed method allow us to reduce such discrepancies for both temperature and precipitation over Europe, even if such more limited improvements were obtained for precipitation. And the overall agreement with Adamant confirmed the fact that we could be able to provide some reliable, tailored information to be used as input by end users for specific applications. So we used such calibrated forecast, and we integrated them in the runoff predictions for the study catchment, and we assessed the added value of such forecast for the management of the hydropower production. So now I leave the floor to Mattia, who will talk about this second part of the work. Thanks.
Thank you very much, Alice. So we will now see how we applied this downscale seasonal forecast for the runoff seasonal for the seasonal forecast of the runoff, and with the main objective to produce reliable inputs for the hydro tool model, that is this model that Alperia is using for the hydropower plant management, specifically in the Ultem Valley. But even if we focused on this specific catchment, we were trying to implement the method in a way that it can be easily extended to other areas. And that's why the ERA5 dataset and the seasonal forecast downscaled on the reanalysis of ERA5 was very attractive for us. So in general, when we speak about forecast of the runoff, we have to estimate two sets of variables. The first set is related to the so-called catchment state variables, which tell us how much water is stored in the catchment just before the forecasting period start. And these are like the soil moisture or the soil water, snow water equivalent in the catchment. And then we have to estimate all the variables that give a positive or negative contribution to the runoff during the forecasting period. And these are, for example, the rainfall, the snow melt, and the evapotranspiration. So in general, if we use a physical-based hydrological model, what we have to do typically is to really go and estimate every single variables that I showed before, and this could be a problem in particular catchment because of data availability. That's why sometimes statistical models are more attractive for doing this kind of forecast, because with this statistical approach, you can just select some proxy variables that are somehow related to the catchment state and the contribution during the forecasting period, without the need to go and exactly estimate each single variable. So in particular, the proxy variables that we selected are simply the temperature and the precipitation from ERA5 and the seasonal forecast downscaled on ERA5. And this choice is driven by the fact that temperature and precipitation are both related to the catchment state, since time series of temperature and precipitation are related to or can describe the amount of water that is accumulating and therefore stored in the catchment before the prediction period start. But temperature and precipitation are also related to all the contribution, positive and negative, that we can have during the period in which we want to do the forecast. As the statistical tool that we used, we selected a machine learning method, and that is the supervector regression, which is a method that has a couple of advantages with respect to other regression algorithms. In particular, supervector regression can easily handle multiple features. And second, supervector regression can also solve highly nonlinear problem without assumption on the distribution of the data. This is quite important for the problem that we are facing, since the relation between temperature and precipitation could be highly nonlinear depending on the particular problem. This is the general workflow of the method that we implemented. So it can be divided in two phases. The first is the training phase, in which we just use time series of temperature and precipitation extracted from the ERA5 reanalysis and target runoff that is estimated by in situ measurements to train our machine learning model. For doing this, we firstly have to select the optimal time series length of temperature and precipitation that can better describe the catchment state before the forecasting period. Once we selected this, we can actually train the model. And once we have the model that is trained, we can go on the prediction phase, in which we combine ERA5 reanalysis and downscale the seasonal forecast of temperature and precipitation for the estimation of the seasonal forecast of the runoff. So in order to evaluate the performance of the method, we focused on the catchment Valentina showed in the Ulten Valley, and we use as a benchmark method the runoff climatology, because this is the methodology that Alperia was using as input to their model to optimize the hydropower plants. We set up a live 1 year out cross-validation strategy, where iteratively we train the model with all the year of training except one, and then we tested the performance on the excluded year. And we also tested the limit of applicability of the method with respect to the availability of time series length of the runoff. So I will go fast here because this was already presented by Valentina, but just to say that we focused on a sub-catchment of the Ulten Valley, so the catchment closed after the Vocolo Lake. And as we can see in the next slide, this catchment is covered by 2 ERA5 grid. And here you can see just an example, an overview of the values of temperature and precipitation of ERA5 on this 2 grid cell. While in the next slide, we see the time series of runoff that we used during the for training the data. That is actually this is the runoff available for training our method, so runoff from 1992 to 2017. So in the next slide, we see how we run the model. So first we selected, so we found the optimal time series length of temperature and precipitation that is needed to describe the catchment state for this particular catchment, and this was identified by 7 months. Finally, in the next slide, we see an overview of the overall results in terms of root mean square error in y-axis. While on the x-axis you see the time series length of the training dataset of the runoff, for which we repeated the simulation. So we trained the model using a different time series length, so from 1 to 26 years. In the black line is the root mean square error achieved with the benchmark methodology, that is the runoff climatology, that was computed using the same years available for training the machine learning model. While with the red line, we see the error of the so-called perfect forecast, in which all the seasonal forecast of temperature and precipitation have been substituted by the actual value of the ERA5 reanalysis. So as expected, you can see that the longer is the time series length of the training, and the lower is the root mean square error. And in different color, you can see the results obtained with different lead time of the forecast, so from 1 to 6 months. And as expected, the higher is the lead time of the forecast, and the higher is also the error. But in general, for all the lead times, so from 1 to 6 months, we are in general below the error done with the benchmark, that is the runoff climatology. So now in the next slide, I will leave the floor to Valentina again, that will show how Alperia was using the results coming out from this model for their application.
In the last slides, I want to summarize some of the results that we obtain by using the forecast data runoff that Europe gave us. So in this first one, in this figure, you have the comparison between the production that is resulting from our model, the HydroTool model, by considering as input the real data that we had in that period and that we measured, and the results are in the yellow bars, while the black bars are the results, the forecast that we obtain by considering the historical mean, that is the climatology data as input of the model, and the last one, the orange bars, are the results by using the forecast data of runoff. In this case, you can see the period that I plotted is from February to July, and this is the results for the single hydropower plant of San Pancrazio. And you can see how also in this case we have a better agreement of the data between the forecast and the real with respect to the climatology that we are using at the moment. In the next slide, you have the same results from the same period for the total production of the valley. And in this case, the results are also more important. In my third slide, you can see the same results, the same comparison, but for a period going from April to September. And in this case, you can see how the forecast is in agreement with the real data, and it produced the lack of production, while the climatology doesn't. And in the next slide, you have the same comparison from the total production. So for concluding, in the last slide, in terms of quantities, more or less, we have differences between the actual production and the production that we obtain from the average data from the climatology of about 30% of production, while both for the single hydropower plant and for the total valley, while the difference between the actual production and the forecast production is the 10% if we consider as input the forecast runoff. In terms of earnings, this could be mean that for the single hydropower plants, we can pass from a disagreement of a differences in percentage of 20% by considering the climatology data and 8% by considering the forecast data. And for the whole valley, the results are more or less the same. We have differences of earnings of 25% by considering the average data and 9% by considering the forecast data. It means that if we take the forecast data as input of the model, we don't have clearly at 10% of security that we could understand which is the production and the consequent earnings from the production of our hydropower plants, but we can reduce the differences between the forecast and the reality. And this is, I think, that it's the main results of our project.
The critical aspect of the weather, that weather variables can affect the business through the hedging strategy. So it's crucial for a corporation like Enel to have tools, practical tools that make easy to access the weather variable. Weather variables, so the weather variables are not easy to use and not easy to access even for non-skilled people, so people that have no strong knowledge on meteorology and so on. So when we tell about trial services, we tell about technologies, so tools, and also I would say consultation. So people skilled that tell to you what they expect and how to use properly the weather data. So basically in SECLI firm, we take technology that already existed previously and we adapt it to the special needs of Enel in order to make available the ERA 5 and the seasonal forecast data easily to our people, especially for traders and economists. Again, the critical point is that they are used to use one-dimensional data for time and the variable. So they are not very easy to use geographical geolocated data. That seems a simple point, but it's not simple. So for them, it's not very simple. So this tool is able to access easily in a easy mode access to the data for anyone to make analysis. So basically, it does the geographical aggregation by country in this example in automatically for ERA 5 and for the seasonal forecast. And you can choose the variables, and basically you can then download the data as CSV file and also to see the plot. An evolution of this tool is also to include the short-term forecast, because for us it's crucial. We cover all the time spans from day by day up to seasonal time span. So basically we included also the NOAA short-term forecast in the tool, aggregated in a special way for Enel. For example, in the United States, we use the domains called gas market domains and power market domains. So they do not consider with the states or counties, but they are special domains for people that work on the markets. So you see the center, the flux. So basically, it will take the data by Copernicus for ERA 5 and seasonal forecast, and by NOAA for the short term. They ingest the data. They make this post-processing for adaptation over our domains and needs, and will deliver the data as easy to use GIS as well as to fill a database. And that's so a first example of the trial service, a direct consequence of the project. So it is a practical outcome, a very important outcome of the project, in order to make easy to use the weather variable. And to make easy to use is important as well as to just have the data. So the data needs to be easily usable. So these are general conclusions from our point of view. So basically, it seems from all the other case studies for Enel that the seasonal forecasts are able to reproduce the signals, but often they are very weak. So the signals are some case too weak for to be captured properly by our industrial and econometric model. Also, SECLI film was a very important project to take the basic know-how on a quite new technology like seasonal forecast. But our point of view as a stakeholder is that we still needed an important effort on the fundamental scientific research. So the instruments are very promising, but maybe they still need a strong support by public academic research funding, especially for mid-high latitudes, where we know that the skills are not really still the best, so especially for rain. So for tropics, they're already fine. But we need, I guess, also still strong support by funny research. Thank you all. That's all for me. Thank you for your attention.